Yeah. Thank you very much for the introduction. It's a great pleasure for me to be here. So I'd like to thank the organizers. Vienna is a lovely city, and the conference has been really inspiring for me so far. So I'm going to present a joint work with Gilles Carron from Nantes Université, Ilaria Mondello from Paris-Créteil. And so this work falls into the framework of a project that has resulted in 4 papers. So let me first just give you the story of this project. So we have 4 papers. And the first 2 were dedicated to the structure of some limit spaces that we called Dynkin, Kato, and strong Kato. Spaces. The third one was dedicated to questions of torus stability in this context of Kato bounds. I'm going to, I will give the precise definitions later. And today I'm going to talk about this 4th paper that actually gives so a relation between Kato bounds and the Bakry-Émery curvature dimension condition. And it turns out that this 4th paper improves the results of the 2 first. So that's to set up the. It work well? Do you hear me well? It's fine. Okay. Not really. You don't. Oops. It should be fine now. Is it better? Okay, great. Oops. Okay, so in order to present the relationship between Kato and Bakry, let me give you one aspect of Kato bounds. So one aspect is really the one that we were driven by actually a initial work of Gilles Carron. And his motivation came from a theorem from Philippe Castillon in 2011 that says that on a smooth, complete, non-compact surface, this condition, so non-negativity of the Schrödinger operator with potential multiplicative constant against the Gaussian curvature, if we assume that this operator is non-negative, then we have a control on the volume of balls on the space. Okay? And so Gilles was interested in trying to find generalization of this initial result. So he looked for a statement of that kind, so make some assumption on a Schrödinger operator on a manifold of dimension n, arbitrary dimension n, a Schrödinger operator with a potential involving some curvature, and obtain a volume estimate. And so in the paper we presented this work, he showed the answer was yes with, if you take as curvature potential this function that I'm going to define in a minute, reach minus of g, and the assumption of the Schrödinger operator was a gaugeability assumption. So gaugeability was mentioned this morning by Professor Kouae. I'm going to give, let's say, one aspect, so one I'm really interested in. And so this, yeah. Let me also mention that Christian Rose, at the same time as Gilles, investigated the same kind of assumption on the potential and obtained a result that eventually leads to the volume estimate that Gilles obtained in the closed case, under the condition that manifold is compact without boundary. Okay, so this function reach minus j is just a negative part of the lowest eigenvalue of the Ricci tensor. Okay, so you take the Ricci tensor, you take the lowest eigenvalue, it gives you some function from m to 0 plus infinity, from m to r, sorry, and you take the negative part of this function, so I draw elementary picture here. So the line here is a manifold. The orange curve accounts for the first eigenvalue of the Ricci tensor, and the blue curve is our negative part of this eigenvalue. So this function provides us the optimal non-negative function satisfying this bound on the Ricci curvature. Okay. Now I'm going to give you a definition. So, yep, a definition that works for me on Riemannian manifolds. A Schrödinger operator, I say that it's gaugeable if there exists some smooth function that is such that the Schrödinger operator applied to this function gives me 0. And I want this function to be bounded, so between 1 and gamma. Okay. And I also introduce, for the matter of clarity, let's say in my talk, where we'll focus more on parabolic aspects, this notion, parabolical gaugeability. Let's say that there exists some time t such that for any initial function u naught, there exists a smooth solution on m times interval 0t that stays bounded. So my function is between 1 and gamma. Okay. Yes. Yes. So yeah, u0 must so be at least 1. Sorry. Okay. And so now these are the results that Gilles gave in his paper. So the first one was explicitly stated and dealt with complete non-compact manifolds. So in the case of non-compact manifolds, he had to add some additional assumption. He had to assume that some Euclidean Sobolev inequality was in force to control somehow the geometry of the manifold at infinity. And under this additional assumption, gaugeability of the potential, so delta minus, I forgot the g here, delta minus lambda, which g minus g, implies Alfors regularity on the manifold. So Alfors regularity means that the volume of balls of radius r is comparable, so bounded from above and below by constant times Rn. It's comparable to the Euclidean volume. Okay, so this is a non-compact case. And so he also had a result in the closed case, so compact without boundary. This theorem was not explicitly stated in his paper, but so again, for the sake of my explanation of today, it's better to explain it in that way, I think. So if this Schrödinger operator is parabolically gaugeable, then the manifold is locally doubling. So the volume of a ball of radius 2r for r small enough, so smaller than square root of t divided by 2. So here, sorry, I'm assuming that's the solution. So this gaugeability means that there exists a solution of some PDE and parabolic PDE. I'm assuming that it is up to time t. Then we get a doubling condition for radius smaller than square root of t by 2. The volume of a ball of radius 2r is controlled by the volume of a ball of radius r. Okay. So this theorem, this result, is especially interesting for people that investigate the structure of limits of Riemannian manifolds, because when you have a class of Riemannian manifolds that are uniformly doubling, you know that by Gromov's precompactness theorem that there exist limit spaces. Okay. Now, Now the reason why the name Kato entered in our work is that Kato type conditions imply gaugeability. So again, this was also mentioned in the talk this morning by Professor Koué. And here, I'm only focused on the only potential on which I will focus is this function Ricci minus j. And I will say that Riemannian manifold, MNG, satisfies a Kato condition if this quantity that depends on T, so what is this quantity? It's the supremum over the manifold, or X on the manifold, of the integral between 0 and T of the evaluation of the relaxation of Ricci minus J by the heat semigroup. Okay. So this morning, Professor Coué used a formalism that was more probabilistic with some expectation. Here I'm using formalism that I'm more familiar with on Riemannian manifolds. And okay, so Kato condition is asks that this quantity that depends on T goes to 0 when T goes to 0. And dinking condition is a condition that is weaker. Just say that for some T, big T, and for some gamma, K at big T of Ricci minus J is less than gamma. Okay, so here I'm only defining. So in this definition, the definition of this KT, you see that the heat semigroup appears. So that's why this function is of parabolic flavor. Okay, I'm only considering parabolic conditions here, but you can cook similar assumptions using so using the green function instead of the heat kernel, and so you will obtain gaugeability and not parabolic gaugeability. Okay. Okay. So now the roadmap of Carron's paper was the following: if you assume that that you have a dinking condition with a gamma that is less than 1 by 16n, then you deduce parabolic gaugeability of corresponding Schrödinger operators, with Ricci minus G here. And to obtain this, it's just a use of a fixed point theorem. So you want to solve a PDE, you transform it into an integral equation. Then to prove that there exists a solution, you look for a suitable operator. And to apply a fixed point theorem, this operator must be contraction. And the condition on this KT actually appears at the level of the norm of this operator. And so if this KT is small enough, the norm of the operator is less than 1, and you can apply a fixed point theorem and get your solution. Okay, that's the idea on how to pass from here to here. Then, from the existence of a solution of this of the corresponding PDE, one can prove some Li-Yao inequality on the manifold, and this is obtained through a paper of Zhang and Zhu from 2018, which, however, requires compactness. So it's just that, okay, to pass from here to here, to obtain this Li-Yao inequality, at some point, Zhang and Zhu uses a maximum principle that, that you can perform on if your space is compact, but that does not work if the space is not compact. Okay, so this is why there was restriction here, that the manifold should be closed, even closed, not only compact but closed. And then, so this Li-Yao inequality allows to get eventually the volume doubling condition. Okay, so I don't give the details here, but that's main steps on how to pass from this dinking condition to a volume doubling condition. Okay, and so this was the starting point of our investigation in the two first papers. So once we have this volume doubling, so if you have a sequence of manifolds that are uniformly dinking, then we have a uniform volume doubling assumption. We can use Gromov-Hausdorff compactness theorem and obtain limit spaces. Okay. Other questions so far? Okay, so now I'm going to talk about the Bakry-Émery condition, so the other side of the picture. So it's well known by most people here, but let me start from Riemannian geometry. So I always start from Bochner's inequality, Bochner's equality. Let's say that on a complete Riemannian manifold for any smooth and compactly support function, this equality holds. So we have here a term that always depends on your sign convention of the Laplacian, and here a term that that involves the equation of the function and the Ricci curvature. And so the Ricci curvature term can be bounded from below by minus Ricci minus du square norm. And this, I think maybe I've made a mistake. Oh, it's fine. So it's just by right. So you can actually you can turn the Bochner equality into a Bochner inequality, and this is the starting point of the Bakry-Émery theory that was developed in the that was introduced in a paper from 1995, and so today we'll only focus on the case of weighted Riemannian manifolds. So on weighted Riemannian manifolds, you just add some weights in front of the volume measure of the manifold, some positive weights, and you say that this weighted manifold satisfies Bakry-Émery Kn curvature dimension condition if you have a similar Bochner inequality, but with the Laplacian replaced by the corresponding Laplacian that you obtain if you want to that you get if you want to have a proper nice integration by parts formula. Okay, so it's just the Laplacian of the weighted Riemannian manifold. So the Laplacian by Laplacian, I mean the operator that gives you a nice integration by part formula. And you have k that appears here and n that appears here. Okay. So really quickly, so Bakry-Émery Kn implies both doubling and Poincaré inequality. In particular, if you have a sequence of uniformly Bakry-Émery weighted Riemannian manifolds, then this sequence is uniformly doubling. Again, you obtain precompactness and you have limit spaces. The condition, the Bakry-Émery curvature dimension condition, can be also defined in suitable metric Dirichlet spaces. So the first talk of the conference was about that by Pate. Under suitable assumptions, when I say suitable, it's just okay. And you need to make sure that it's better. Okay. Well, essentially, the Bakry-Émery curvature dimension condition is equivalent to the RCD condition, so formulated in terms of optimal transport and calculus on Sobolev calculus on metric measure spaces, and this the latter condition is stable under pointed measure Gromov-Hausdorff convergence. So here the limit spaces that you would obtain would also be Bakry-Émery, would also satisfy the Bakry-Émery curvature dimension condition. Now, okay, so let's make them discuss together. So for the first, yeah, what we wanted to do was to try recover some uniform bounds on Ricci, weak uniform bounds on Ricci, starting from Dinkin, Kato, or strong Kato condition. In dimension 2, it's rather easy to do it. So if you work on a smooth surface that satisfies this Dinkin condition, then you can always, you can transform, you can find a conformal metric, which is comparable, nicely comparable to the original metric, and whose Gaussian curvature is bounded from below. Okay. So let me explain why. So if you write G tilde as E minus 2 phi G, then the classical formula for the transformation of the Gaussian curvature under conformal change gives you this. Then Kg, the Gaussian curvature, you can bound it from below by minus Kg minus. And now what you want to obtain, you want to show that this is less than some constant. So you need to find a suitable function phi, which allows you to write this as some minus 1/2 phi. You need to. Okay, so right here, so you have minus E phi minus Kg minus, that is equal to minus 1 by T phi. And if phi is bounded from above, then this is bounded from below by minus C over T. Okay, and so the existence of such a phi is again a question of gaugeability, and we can obtain it also under this the Dinking condition. Okay, and so for dimension 2, it's easy. There is no need to have Bakry-Émery in the picture. And now for higher dimension, well, conformal changes must be replaced by other transformations called time changes. So these transformations are probably more familiar to probabilistic people. So as a geometer, it's for me, conformal changes are more natural, but these changes work as follows. So you replace G by some factor, like a conformal factor, right here e to the 2 phi, and replace a measure mu tilde by a different factor than the one that you would obtain from a conformal transformation, and this factor is the same as the factor in front of G. So this transformation gives you a new Dirichlet energy, and this Dirichlet energy actually coincides with the original Dirichlet energy for any smooth and completely supported function on the manifold. So, okay, so it's interesting from the point of view of the energy, let's say, on the manifold. It doesn't preserve the energy structure of the space. And the corresponding Laplace operator will be a factor times the original Laplacian. So this transformation, time change transformation, and also conformal transformation, have been studied by Theo and by Han on singular settings, and actually they provided a transformation law of curvature dimension condition, of the Bakry-Émery curvature dimension condition under time change. Okay, so in our context, in the context of a smooth Riemannian manifold, the transformation law reads as follows. So for any smooth function u and any positive number q, so this term is just the replacement of the term appearing in the Bochner inequality with when you replace the Laplacian by the time changed Laplace operator and the time change metric. Then here, this term is also the same term as the one that appears in the Bochner inequality, but with the corresponding operator. And the big difference is on the, let's say, curvature factor, the curvature term, where you see this second order term appears, which involves a negative part of Ricci, the Laplacian of phi, and the square norm of d phi. And now if I compare this with the Bakry-Émery k by t n condition, then, well, so this Bakry-Émery kt, I just have to put k over t here. And now, so if I want to pass from a smooth manifold to a weighted manifold, so smooth manifold with Kato to a weighted manifold with Bakry-Émery, I need to choose a suitable phi to make sure that this term, blue term here, is bounded from below by this constant. Okay, and this choosing phi in a suitable way is ensured by the linking condition. So this is a theorem, main theorem on this fourth paper on a complete Riemannian manifold. So insist on the fact that the manifold need not be compact, need not be closed. Complete Riemannian manifold. If the manifold satisfies the linking condition where the constant gamma is less than 1 divided by n minus 2, then there exists weighted Riemannian manifolds obtained from M by time changed, which satisfies the Bakry-Émery k by t n curvature dimension condition. And this phi, so again, we obtain it by gaugeability. So this phi is this phi is bounded from below by 0 and from above by some constant. So this factor here is bounded from below by 1. So maybe always sign. Okay. And some comments on this on the values that we obtain, k and n. So k and n, they both depend on n and gamma, n being the small n being the dimension of the manifold, and gamma this linking constant, say. So when gamma goes to 1 by n minus 2, we see the curvature explode to minus infinity. Okay. When now concerning big N, so big N is always bigger than small n. It's not necessarily an integer. And when gamma approaches 1 by n minus 2, it explodes. And when gamma approaches 0, it converges to n. Okay, so let's say the lowest this quantity is, the closest we are from the original dimension. And yeah, last point, that's since we have this control from above and below on the gauge function, then actually we have B-Lipschitz equivalence between the distance coming from the original Riemannian metric and the time change Riemannian metric, but also equivalence of the measures. So the measures are absolutely continuous one with respect to the other, with bounds on the densities. Okay. And so now let me explain how this result improves our previous results. So in our first paper, as I said, we consider only closed Riemannian manifolds, and we assume that these closed sequences of closed Riemannian manifolds satisfying a uniform linking condition. We call this the limit spaces obtained in this way. So sorry, the O here need not be. Yes, sorry. No, we didn't assume a bound on the diameter. So closed Riemannian manifolds, but possibly with diameter that explode, converting to a limit space, and we call these limit spaces linking limit spaces. So the first result is that we can remove closed here. We can remove closed because so the previous result says that linking implies B-Lipschitz equivalence to a spaces satisfying Bakry-Émery condition. So this Bakry-Émery condition implies uniform doubling. And so if you are B-Lipschitz equivalent to a metric space that is uniformly doubling, then you're also uniformly doubling. If you have a sequence of spaces which are B-Lipschitz equivalents to all B-Lipschitz equivalent to spaces which are uniformly doubling, then the original sequence is uniformly doubling. Okay. We can remove closed. Now, the second statement, so these Dinkin limits, still with gamma less than 1 by n minus 2, any of these Dinkin limits is actually B-Lipschitz equivalent itself to an RCD k by t n space. Okay, and in particular, we can use the structure results on RCD spaces to improve the results that we had on limit spaces, on Kato limit spaces, Dinkin limit spaces. So for instance, we obtain rectifiability. We obtain that these Dinkin limit spaces are all rectifiable with a constant essential dimension. And this is a strong improvement over a result from our second paper, where we could prove only rectifiability of Kato limit spaces. So Kato limit spaces are spaces that satisfy a uniform Kato bound. So this should be a small t here. So the kt over the manifolds goes to 0 uniformly. Okay, so it's a stronger requirement that we put that we ask to our sequence of manifolds, and so in this context, in the context of Kato limit spaces, we obtain rectifiability, but we couldn't prove the constancy of the dimension. So here that's great because we obtain the constancy of the dimension, but for a larger class of limit spaces. So we're really happy when we obtain this result. Yeah, also because the way to prove constancy, so we wanted to mimic tools from RCD theory, but we had no optimal transport tools on our Kato limit spaces. So it was what would be a definition of Kato space with optimal transport. It would have been too difficult. So it's good to have a hammer that kills problems. And so now we had another result that concerned so the class of strong Kato limit spaces. And so this class, for this class of spaces, we ask that the convergence to 0 of this, I forgot the t here, of this uniform kt satisfy this integrability assumption. So honestly, we don't fully understand the meaning of this assumption. It's just that it is technical, it works well, and so it says that f of t must go to 0 quickly enough to ensure that this function f of t by t is integrable at 0. And well, when adding this assumption, actually we obtained most of the structure results of Gilles encoding for non-collapsed Ricci limit spaces. And one result we obtained was a version of the following. So let me give the statements. So any non-collapsed strong Kato limit space. So non-collapsed means that the dimension of the limit space is the Hausdorff dimension of the limit space is the same as the Hausdorff dimension of the approximating manifolds. It satisfies the following. So for any epsilon, there exists some delta such that if the volume ratio of a ball centered at X with radius R is close enough to the volume of the Euclidean ball of radius R, so close enough in the sense that it is more than 1 minus delta, then the ball of half radius, so R by 2X, is Reifenberg regular. So it means that small balls at any scale on our ball R by 2X are Gromov-Hausdorff close to a Euclidean ball of same radius. Okay, and this in particular, this implies by intrinsic Reifenberg theorem of Gilles encoding the existence of Beelder charts actually around our point X. Okay, so we have a structure of Beelder manifolds of the set of points X that are nice enough, that are close enough to being Euclidean. And in our paper, in a second paper, we obtain a similar result, but instead of having the volume ratio here, we had another ratio that was more suited for our purposes and our context, let's say. It's a ratio of heat canals. So here H is the heat canal of the manifold, or the space here, the limit space, heat canal at time t and point xx, divided by the value of the Euclidean heat canal at point xx. So in the heat canal, Euclidean heat canal, you have some Gaussian term that disappear when x is equal to y, and so you only get a constant. So so we prove the theorem with this heat canal ratio, and the theorem that we obtained, this time change to Bakry-Émery, actually allow us to come back to more classical results, say classical results in the sense that we use the volume ratio that has been used by Chigurh-Colding and the people working on this kind of questions. Okay, and well, that's all I wanted to say. So thank you.